Hello, my dear students. Welcome to Learning Chemistry is Easy and Fun on YouTube. The topic that we are taking up today is called as the laws of chemical combination, one of the basic chapters that we begin with at the AS or the class 11th level. The three laws, in fact, four laws that we are going to study today, the laws of chemical combination. The first one is the law of conservation of mass. The second is the law of constant or definite proportion. The third one is the law of multiple proportion. Let us start with the law of conservation of mass. What does the law of conservation of mass say? Now, this is very much similar to the law of conservation of energy, which you have done in your previous classes. Can you recall what does the law of conservation of energy state? Here you'll have some blank space. Now, how are you going to use the blank space? What you have to do is you have to get hold of a pen and paper so that you can make a note of whatever is being taught in this particular video, and they become your notes for offline reference. See, so easy. So you would have understood the topic as well as you would have notes by the end of this video. So write down the law of conservation of energy in this space and then continue with the video. Law of conservation of energy. Energy can neither be created nor destroyed, it only changes its form. Absolutely same, the law of conservation of mass. Mass can neither be created nor be destroyed, it only changes its form. We burn a substance. For example, candle. It burns to give you carbon dioxide, water, and some amount of soot, right? Which is the carbon which has been left unoxidized. So you think that the candle has got destroyed, but what has happened is only the wax has burned to give us the other products. For example, if I say I'm taking ethene C2H4, it is burnt in oxygen, gives me carbon dioxide and water, right? Now, here since we know that matter can neither be created nor destroyed, the mass of the substances on the left-hand side of the equation should be the same as those on the right-hand side. The substances on the left-hand side are what we call as the reactants, whereas those on the right-hand side are what we call as the products. So on the basis of this law, the total mass of the reactants should be equal to the total mass of the products, and that is the principle on which we balance a chemical equation. So 2 carbon on the left hand side, so we will make it as 2 carbon on the right hand side. Would you like to do it yourself rather than just watching? Give it a try. Pause the video. Give it a try yourself. Yes. So we will have 2 carbon dioxide, 4 hydrogen. So we will have 2 water. 2 times 2, 4 plus 2, 6. So we will have 3 oxygen. Now, this was given long back by Lavoisier, sometime in the year 1774. Now, we know that science has undergone a big change over the years. And what came in between was the Einstein's theory. Let's talk about that. Einstein's mass-energy relation, which says that mass gets converted into energy, and the relation that he gave was E is equals to mc square, right? And that is the basis of the nuclear energy that we talk about. The destruction of mass releases energy. Now, when we are talking about the destruction of a small amount of mass, for example, an atom, the amount of energy released is very, very small and very negligible. But when we are talking about a nuclear reactor, then in that case, since the destruction of mass or the amount of energy that is being released by the destruction of mass cannot be ignored, we modify the law of conservation of mass in the modern context. So, what do you think we can do in order to club the law of conservation of mass and the law of conservation of energy? Give it a thought. Yes, the sum total of the mass and energy of a system remains constant. So we don't see mass and energy in isolation. We have clubbed them together. But you need to understand that this is applicable more on a microscopic level, on a subatomic level to be more exact. When we are talking about our normal laboratory experiments, that means we are talking about the macroscopic systems. In that case, we still stick to the rule that the total mass of the system is conserved, and that is the basis on which you balance your chemical equations. Would you like to practice a few questions based on this? Now here I've got a very simple question for you. We have a reaction where sodium bicarbonate reacts with acetic acid to give us a salt, that is sodium acetate, water and carbon dioxide gas is released. The question is that you have been given 6.3 grams of sodium bicarbonate. The amount of acetic acid that we are using in this particular experiment is 18 grams. If it is given to you that the weight of the residue is in all 21 grams, then what is the amount of carbon dioxide liberated in this particular reaction? So let's see. 21 grams, you have to remember, is residue. Now what do we have in the residue? In the residue, we will have sodium acetate and water. These are part of the residue, right? So what is the total mass of the reactants that we've got over here? 18 plus 6.3 gives me 3, 4, 2, 24.3 grams. Whereas the mass of the products that I've got till now is 21 grams. Now, according to the law of conservation of mass, the total sum of the masses on the left-hand side should be equal to the sum of masses on the right-hand side. So, 24.3 should be equal to 21 plus X, where X is the mass of carbon dioxide. So, what will be your answer? And please don't forget the units, right? Should we go on to the next law? The next law, law of definite or constant proportion. I'm going to take a very, very simple example over here. Water. You take water from your tap, you take water from the river, you take water from the ocean. Purify it, distill it. Now find out the ratio of hydrogen to oxygen in each of the 3 cases. You will find that every time, irrespective of the source, the ratio of hydrogen to oxygen in each of the samples of water would be 2:1. In other words, water is made up of 2 parts of hydrogen and 1 part of oxygen. If I am talking about water, if let us suppose the ratio of hydrogen to oxygen becomes 2:2, or simply put 1:1, am I still talking about water? No, we are talking about hydrogen peroxide in this case, right? So what does the law of definite or constant proportion say? It says that if we are talking about a pure chemical compound, irrespective of the source from which we are obtaining it, you could obtain water as part of the product of burning of hydrogen also, then the ratio of the elements that are combined together always remains the same. That is why the word constant or definite proportion. So if we are talking about water, the ratio of the 2 elements will always be 2:1. Can you please define this law for me and write it in your notebooks? Again, it will become easy for offline reference. Let's take up a question over here. We can obtain magnesium oxide by 2 different ways. So I've gotten the first set of experiment where we burn magnesium in oxygen to give us magnesium oxide. Of course, you can balance this equation 2 and a 2 over here. The second experiment is where we've got magnesium carbonate, which on heating gives us magnesium oxide plus carbon dioxide. Magnesium, the amount of magnesium being burnt over here is 2.4 grams, and the amount of magnesium oxide which we obtain is 4 grams. We do not know how much of oxygen we have used. On the other hand, in the second experiment, the data provided to you is that on heating magnesium carbonate, we've got magnesium oxide, which on analysis is found to contain 60% of magnesium and 40% of oxygen. So, which law is depicted by this particular experimental observation? Now, we know that it's the law of definite proportion, but how are we going to prove it? Because we know it's a law of definite proportion because that's the only law we've done till now, right? So first of all, we know that over here magnesium is 2.4 grams. Magnesium oxide is 4 grams. So what is the weight of oxygen that you've got over here? Perfect. 4 grams minus 2.4 gives you 1.6 grams. So what is the ratio of magnesium to oxygen by weight over here? Yes, it is 2.4 divided by 1.6. Would you like to simplify it for me? Can you give me a simpler expression? Yes, do away with the decimals. 8 times 3 is 24 and 8 times 2 is 16. So the ratio of magnesium to oxygen as determined by this experiment, the first one is 3:2. Let us take the second case. Now here both the values are given to us as a percentage. So let us determine the ratio of magnesium to oxygen. So 60:40. Correct? Again, that is simply 3:2. So if you see the ratio of the elements by weight in both the cases is the same. Thus, it portrays that the law of definite proportion is valid for this particular experiment. Would you like to try 2-3 more questions yourself in order to make this concept clear? Go ahead, give it a try. Now let's talk about the law of multiple proportions. That means we are talking about more than one type of compound. So I've taken a simple example over here, water and hydrogen peroxide. Now when hydrogen and oxygen are combining with each other, they are giving me two different compounds. The amount or the weight of hydrogen in grams in H2O is 2 grams of hydrogen, and the weight of oxygen is 16 considering their atomic masses. Let's see what is there on the right hand side. Now here there is 2 grams of hydrogen and it is combined with 16 into 2, that is 32 grams of oxygen. So the ratio of hydrogen to oxygen over here is 2:32. One of the elements is taken constant. So let's suppose I am taking 2 grams of hydrogen as constant. In the case of water, 2 grams of hydrogen is combined with 16 grams of oxygen, right? In the second case, 2 grams of hydrogen is combined with 32 grams of oxygen. 2 grams of hydrogen is constant in both of them. So let us find out the weight of oxygen in each of the two cases, which is combining with a fixed weight of hydrogen, and that is 2 grams in this case. So we will say the ratio of oxygen combining with 2 grams of hydrogen would simply be 16:32, which is equal to 1:2, meaning to say that the weights of oxygen in each of the two cases which are combining with a fixed weight of the other element bear a simple ratio to one another. We are talking in terms of weights here as well. I would be happy if you can define this law for me and make a note of it in your notebook. Again, for offline reference, go ahead, please do it. Let us start a question again based on the law of multiple proportions. We're talking about two experiments, experiment 1 and experiment 2, wherein we've got oxides of carbon. We don't know whether they are same or different, and these are analyzed, and each one of them gives us this data, wherein the first one, the percentage of carbon is 42.9%, whereas in the second one, the percentage of carbon is 27.3%. So which law is depicted in the above observation is what we have to see. So since these are oxides of carbon, that means they are made up of only carbon and oxygen. So if I know the percentage of carbon, I can determine the percentage of oxygen as 100 minus 42.9. Can you please do the calculation for me and give me the answer? Same way, oxide of carbon, we know the percentage of carbon is 27.3. So the percentage of oxygen over here would be 100 minus 27.3. So this gives us a value of 57.1, right? Do our answers tally? And here the value would be 72.7 grams. Now you have to see whether the ratio of the oxygen which is combining with the same weight of carbon, whether that ratio is 1:1 or some multiple of it. If it is 1:1, that means it is the law of constant proportion. But if it is some multiple of it, that means it is the law of multiple proportions. Now, if you see over here, the percentage of carbon in both the cases is different. So how do I compare? We can't compare 57.1 and 72.7 because we are not talking about the weights of oxygen combining with the same weight of carbon. So we need to take some constant. So let's suppose the constant that we are taking is 1 gram of carbon. So if we have, let me do it like this. So if we have 57.1 grams of oxygen combining with 42.9 grams of carbon, then how much of oxygen will combine with 1 gram of carbon? Nothing, no big deal. I have simply used the unitary method. Instead of writing full statements, I have written it as a ratio. So what is the value of X that you get over here? I would love to see you calculate these values and give me the answer, because then the lesson becomes interesting. Otherwise, you lose interest very soon. Again, second case, carbon and oxygen. We know that 72.7 grams of oxygen is combining with 27.3 grams of carbon. So, how much of oxygen is combining with 1 gram of carbon? This is what we mean by taking constant. What is the purpose of taking it as constant? It is to ensure that we are comparing it with the same fixed amount of the other element. So in the first case, what is the value that you are getting? 1 point something, 1.331. In the second case, the value that you get is approximately 2.662. You could also take it as just up to 1.33 and 2.66. So let me make things a little bit easy for you. So 1.33 and 2.66. So this is the weight of oxygen that is combining with 1 gram of carbon in the first case. And this is the weight of oxygen which is combining with 1 gram of carbon in the second case. 1.33 is to 2.66. What is the ratio? It's a simple ratio, 1:2. So which law is obeyed in this particular? Yes, it's the law of multiple proportions. Interesting till now? You want me to stop or you want to continue? Would you like to do one more law? Okay, last law in this particular lesson. It's a small law, Gay-Lussac's law. When gases combine, first and foremost thing in this law is we are going to talk only about gases. When gases combine, they do so in volumes. We are not talking about the mass, which bear a constant ratio to one another and to the volume of gaseous products formed. When you are measuring all volumes at constant conditions of temperature and pressure. Now in this particular law, this expression, constant temperature and pressure or same condition of temperature and pressure, is very, very important. Why? You will see in the next chapter that the volumes of the gases, they change with temperature and pressure. So when you are stating this law, make sure that you specify the condition for it. Let's see a simple case. Hydrogen gas combining with chlorine gas gives you HCl gas. The volumes will bear a constant ratio to one another. So if I have 1 liter of hydrogen, I will need 1 liter of chlorine, then the amount of HCl formed is 2 liters. The ratio is also to the volume of gaseous products formed. So we see the coefficient here, 1, 1 and 2. So supposing I say that I have to convert 10 liters of hydrogen to HCl, how much of chlorine is required and how much of HCl will be formed at the end of the reaction, considering that the reaction goes to completion. So very simple, we've got the ratio of 1 is to 1 is to 2. So 10 is to 10 is to 20. Simple. Try one more question. I've got hydrogen gas burning in oxygen gas to give us steam, H2O, in the form of a gas or vapor. So if I have to burn 2 liters of hydrogen, how much of oxygen is required and how much of steam will be formed, assuming the reaction goes to completion? First and foremost, we will balance this equation. Now see the ratio. 2 is to 1 is to 2. So 2 parts of hydrogen combining with 1 part of oxygen is equals to 2 liters of hydrogen requiring how much of oxygen? Go ahead. Yes, it will be just 1 liter, right? Have you noted this down? Because I am going to erase it from the board. It should come in handy for your future reference. Right? So what do we have over here? We will have 1 liter of oxygen being required in the gaseous form. What about steam? How much of steam will be formed? Again, take the ratio. 2 is to 2. So 2 is to 2. 2 liters. If, let us suppose, instead of the gaseous form of water, it was written over here H2O liquid or solid, do you think we could apply the Gay-Lussac's law? Think about it. See the definition and then tell me, do you think we can apply the Gay-Lussac's law in such a state if water is a liquid? No, we cannot. Why? Because the law clearly states that it bears a simple ratio to the volume of gaseous products formed. I hope this makes the things clearer to you. If you've been able to relate what is being taught, please don't forget to give a thumbs up. It'll help me to be more confident and to work towards helping you all. Don't forget to press the bell icon to be notified of future videos being loaded. And the best of all, please try and teach this topic to one of your classmates or your friends in order to see the smile that you can bring to somebody. And don't forget to share the channel with friends and classmates to spread this happiness. Stay safe, stay healthy.